Today we're going to be deriving the approximation for the electric field due to a uniformly charged disk. So looking at our disk, we can see that it's composed of many rings. For our integration, our interval is going to be from the origin of the disk, which is going to be the center, which is 0, 0, to our most outer radius or outer part of the disk, which is going to be our r. What's changing in our disk is going to be our delta r, and then our r is going to be considered our arc length, which is going to be given by the 2 pi r. So our electric field is going to be coming from the center of the disk, because at the center of the disk, that's the electric field is the most uniformly charged throughout. So when we do our delta E, we're going to see our 2 pi r and our delta r. Our delta r is going to be what's changing in our 2 pi r is our circumference of the circle. So the 2 pi r times the delta r is going to give us our area of the disk. So the center ring is going to be at the origin, so our r is going to be 0, 0, z. The z is from the center to the location of where you want to calculate the electric field. So doing the magnitude of the r, we're going to get our magnitude is equal to z, and the r hat is going to be 0, 0, 1. So then we can use the thin ring approximation formula. So E equals 1 over 4 pi epsilon naught times qz divided by r squared plus z squared to the 3/2. We can solve for our q, our delta q, which is going to be equal to q times 2 pi r times dr divided by pi r squared. Looking over here, our delta q is just the q times the area of the ring divided by the area of the disk. Then we can substitute our delta q, what we solve for delta q, into our equation. So delta E equals 1 over 4 pi epsilon naught times q times 2 pi r dr divided by pi capital R squared times z divided by r squared plus z squared to the 3/2 times our unit vector 0, 0, 1. Our delta r is just the change of our disk, which is just our integration variable, which is our r is the changing, so that's going to be our integration variable. The 2 pi and the 4 pi are going to cancel out, so we're left with 1 over 2 epsilon naught times q divided by pi r squared times z divided by r squared plus z squared to 3/2 times r dr. Where we did our cutting from is from 0 to r, from the center of the circle or the center of the disk to the outermost part of the disk. So it doesn't matter how big the disk is, it's always going to be from 0 to r. So EZ equals the integral from 0 to r to 1 over 2 epsilon naught times q divided by pi r squared times z divided by r squared plus z squared to the 3/2 times r dr. The 1 over 2 epsilon naught and the q pi r squared and z are constant, so we can pull them out, so we're left integrating the r divided by r squared plus z squared to 3/2 times dr. We can apply u substitution, so u equals r squared plus z squared, and our du equals 2r dr. Dividing du by 2, we're left with r dr equals du divided by 2, and the r dr are going to cancel out. So we're left integrating u to the negative 3/2, removing the 3/2 to the top. So u to the negative 3/2 plus 1 divided by negative 3/2 plus 1. So we're left from u to the negative 1/2 divided by negative 1/2. The 1/2 and the du, the 2 that comes from over here, and the 2 that comes from the top when we move the negative 1/2 to the top, cancel out, so we're left with negative 1 divided by u to the 1/2. Then we can substitute back into our equation for u, and we're left with 1 over 2 epsilon naught times q pi r squared times z times negative 1 r squared divided by r squared plus z squared from 0 to r. When we plug in our points of our integration, we get our equation E equals 1 over 2 epsilon naught times q divided by pi r squared times 1 minus z divided by r squared plus z squared to the 1/2. We can substitute a equals pi r squared, which is our area, so we're left with EZ equals q divided by a 2 epsilon naught times 1 minus z divided by r squared plus z squared to the 1/2, and that is our approximation for a uniformly charged disk.